US Physics Olympiad, year 2023, USAPHO, final round. Problem B2. Fast and Furious. A space program wants to accelerate a spaceship to final mass m equal 100 kilograms to relativistic speeds to observe distant stars. They have two proposals to evaluate. Part A. Their first proposal is to use traditional rocket propulsion. A rocket of initial mass m0 and the final mass m that expels propellant with exhaust speed u relative to the rocket will reach a speed v equal u multiplied by logarithm m0 over m. Suppose the desired final speed is Vf equal 3c over 5. In the subparts below, neglect relativistic effects and give your answers in the form 10 power n, where n has at least two significant figures. Question 1. If the rocket has exhaust speed u equal 3.5 kilometers per second, what must its starting mass be in kilograms? Question 2. If the propellant is exhausted at rate 7.0 kg per second, how long does the acceleration take in centuries? Question 3. If the energy density of the fuel is 2.0 multiplied by 10 power 7 joules per kilogram, how much total energy is required in joules? For the rest of this problem, you should account for special relativity. Part B. Another option is to use a spaceship with a constant mass m propelled by light produced by lasers on Earth, with a total power P equal 6 multiplied by 10 power 12 watt. The light evenly impacts a sail on the spaceship and reflects off the sail directly back towards the Earth. Neglecting the orbital motion of the Earth and give all your answers in the frame of the Earth. Question 1. What is the force on the spaceship when the spaceship has speed v? Question 2. How long will it take to accelerate the spaceship to speed Vf equal 3c over 5 in seconds? You may use the integrals on the reference sheet. Question 3. At the moment the spaceship reaches this speed, how much total energy has been used to power the lasers in joules? The following results from relativity may be helpful. First, the Lorentz factor is defined as a gamma equal 1 over square root from 1 minus v square over c square. Second, an object of mass m and the velocity v has momentum p equal gamma mv and energy E equal gamma mc square. The force is defined by F equal delta P over delta T. Third, the momentum and energy of light are related by E equal PC. Fourth, in the frame S prime with a velocity v multiplied by chord x relative to frame S, the energy and momentum are E prime equal gamma multiplied by E minus v px and the px prime equal gamma multiplied by px minus ve over c square. Solution for Part A. Question 1. If the rocket has exhaust speed u equal 3.5 km per second, what must its starting mass be in kilograms? Solution. We can use this expression for final speed to express m0 through other parameters. So that will be m0 equal final mass m multiplied by exponent power v final over u exhaust, which is equal 100 kg multiplied by exponent power 2.2 multiplied by 10 power 4, which is approximately 10 power 22,337 kilograms. So that's answer for question 1. Question 2. If the propellant is exhausted at rate 7.0 kilograms per second, how long does the acceleration take in centuries? Solution. So here we can use formula time equal mass difference, which is m0 minus m, divided by exhaust rate, which is 7 kilograms per second. So finally that will be this expression, or 10 power 22,336 seconds, or 10 power 22,327 centuries. That was answer for question 2. Question 3. If the energy density of the fuel is 2.0 multiplied by 10 power 7 joules per kilogram, how much total energy is required in joules? Solution. Here we can use equation mass difference multiplied by energy density of the fuel, which finally give us 10 power 22,344 joules. That's the answer for question 3. So we finished with the part A. Solution for part B. Another option is to use a spaceship with a constant mass m, propelled by light produced by lasers on Earth, with a total power P equals 6 by 10 power 12 watt. The light evenly impacts a sail on the spaceship and reflects off the sail directly backward the Earth, neglecting the orbital motion of the Earth, and give all your answers in the frame of the Earth. Question 1. What is the force on the spaceship when the spaceship has speed v? This problem could be solved by different approaches. First approach, we can use Earth frame of reference during all the problem. Suppose that we have part of momentum which reached the spaceship is delta p plus for time delta t. This is not the same as momentum which was produced by lasers for the same time, because not all the light reached the spaceship for the same time. Suppose that at the same time it was reflected another momentum of light which is delta p minus in opposite direction. If we summarize these two momentums, we will get total change of momentum for our spaceship. Total momentum for spaceship was P equal mv over square root from 1 minus v square over c square. So total change of momentum for our ship was delta p, which is equal delta p over delta v multiplied by delta v, which is derivative from this part by speed v, which is this expression, and that must be equal to change of momentum for our beam light. So we have this expression. Now let's check what happened to the same portion of energy for this beam light. So we have energy from the light beam which fell on the ship was delta E plus, which equal C delta P plus, and the energy of the beam which was rebounded was delta E minus, which is equal C delta P minus. Kinetic energy for our ship was mc square over square root from 1 minus v square over c square. It means that a change of energy was a delta E over delta V multiplied by delta V, which is this expression. And this change of energy equal energy difference between delta E plus and delta E minus. So using these two expressions for change of energies, we can express them through momentum difference, which is this one. Now we have delta P plus plus delta P minus and delta P plus minus delta P minus. So we can add these two equations to eliminate delta P minus, which we don't need. So we got delta P plus equal this expression. Now we can express delta P plus through our power of our beam. So we have momentum which reached our ship was delta P plus, which is equal energy which was reached by this beam over C. But the energy equal power which reached our ship multiplied by delta T. Power P plus just equal part of power which reached our spaceship. That was power multiplied by 1 minus V over C. And the delta P plus over delta T equal this expression. Now let's write expression for the force. By definition, force equal delta P of our ship over delta T, which is this expression, and using expression for delta P over delta T, which is this one, we can rewrite force in this form, and the delta P plus over delta T equal this one, and finally force equal 2 powers over C multiplied by 1 minus beta over 1 plus beta, where beta is a regular expression for V over C. That was solution for the first question in part B. Second solution for the first question from part B. What is the force on the spaceship when the spaceship has speed V? Now let's do this problem in the spaceship frame of reference. First take beta equal V over C, where V is speed of our spaceship. Let's take a portion of momentum delta P plus, which affect our ship over time delta T. In the frame of reference of our spaceship, this momentum became equal delta P plus prime gamma multiplied by 1 minus beta multiplied by our original momentum delta P plus, and this is according to formula of relativity. In the frame of reference of our spaceship, which is not moving, this momentum reflects with the same quantity and the opposite sign. So that will be delta P negative prime equal opposite delta P positive prime. And now go back to our Earth frame of reference. Again, this momentum became delta P negative equal this one. And now to count what is the total change of momentum for our spaceship, we have to use formula negative delta P minus positive delta P, which is equal to over 1 plus beta multiplied by our original momentum delta P plus. Now let's use expression for our power P. Original momentum produced by lasers was P over C multiplied by delta T, but our spaceship use only 1 minus beta part of this power, so of this energy, because the spaceship moving with the speed v, and we cannot use full power. So we have delta p plus equal original power p over c multiplied by 1 minus beta multiplied by delta t. And finally we have force F equal delta p over delta t, which is equal to 2 powers p over c multiplied by 1 minus beta over 1 plus beta. This is exactly the same answer as in the first solution, which was much longer. Third solution for question number 1 of part B. In the Earth's frame, if the photons in the incident beam have a frequency Fi, then they are reflected with the frequency Ff equal this expression, where we apply the relativistic Doppler shift formula twice, since the photons are first absorbed by the moving rocket and then re-emitted by it with the same frequency. Applying conservation of momentum and using the fact that the momentum of a photon is related to its energy by E equal hf, which is equal pc, we have force F equal delta p over delta t, which is equal to delta n over delta t multiplied by h over c and multiplied by frequency initial plus frequency final, which is equal this expression. Here we have delta n over delta t is the rate at which photons collide with the sail. It is related to the rate at which photons are emitted from the source of Earth by formula 1 minus beta multiplied by delta n emitted over delta t. Finally, since the power of the laser is rate of emission multiplied by energy of photon, which is hf initial, we have force F equal 2 pi over c multiplied by 1 minus beta over 1 plus beta, which is the same answer as for the first two solutions. Question 2 from part B. How long will it take to accelerate the spaceship to speed v final equal 3 over 5 c in seconds? You may use the integrals on the reference sheet. Solution. From previous question we found that force equal this expression. But from other hand we have delta p of our ship is this expression, which finally mc multiplied by delta beta over 1 minus beta square in power 3 over 2. Now we can equalize these two expressions and have this differential equation where we can split variables. So we have this equation which we can integrate and find what is the solution. So we have that total time equal this integral, and from the table given in the additional spread reference sheet we have this integral equal this expression, and when we put limits we have 5 over 3. So finally time equal 5 over 3 mc square over 2p, and that will be 2.25 multiplied by 10 power 6 seconds. So that's the total time, and that was solution for question 2. Question 3 from part B. At the moment the spaceship reached this speed, how much total energy has been used to power the lasers in joules? From previous question number 2, we found that total time equal 5/6 mc squared over power p. So it means the total energy used to power the lasers were 5/6 mc squared, or 7.5 multiplied by 10 power 18 joules. That was solution for question 3 from part B, and here we finish discussion for problem B2.